Hello and welcome to this lesson in our study of linear algebra. Our topic for today is gram-schmidt orthogonalization process. Okay, so in gram-schmidt in this topic, you'll be given a set of vectors, then use this method to find the corresponding orthonormal sets. Okay, that's what we will do today in this lesson. Okay, so let's study the lemma. An orthonormal set U1 up to Un is linearly independent, and for any vector, okay, V, then the vector W is given by this formula, okay, and it's what orthogonal to the set of U, okay. Also, when we consider the theorem, we let V1, V2, V3 up to Vn be an arbitrary basis of an inner product space V. That's meaning of IPSV, inner product space V. Okay, then there exists an orthonormal basis U1 up to Un of V such that the transition matrix from Vi to Ui is triangular. That is, for I starting from 1 to N, our U1 can be written as what we have here. That's AI1V1 plus AI2V2 up to AIIVN, okay, or VI. So let's consider it full. So anytime you have any set of vector, okay, it means that there's another set of vectors such that those vectors are what orthonormal. Okay, so we are going to use this lemma to solve such problems. Okay, so this is the proof of the theorem. That's we set Ui equals to V1 equals to V2, V1 over the norm of V2, sorry. Okay, then Ui is what? Orthonormal. The next one is to set W2 such that W2 is given by V2 minus the inner product, okay, of V2 U1. Okay, then U2 is what? W2 over the norm of W2. Okay, W2 over the norm of W2. The next thing is to set W3, okay, such that W3 equals to V3 minus the inner product of V3 U1, okay, then U1 minus the inner product of V3 and U2 times U2, okay. So generally, Wi plus 1 is given by Vi plus 1 minus the inner product of Vi plus 1 U1 up to the last term is given by the inner product of Vi plus 1 minus Ui, then Ui. Then the Ui plus 1 is given by the Wi plus 1 divided by the norm of Wi plus 1, such that the norm of Wi plus 1 is non-zero. Okay, so now let's solve an example. Let's solve an example. So we have a matrix. This is a 4 by 3 matrix. Okay, given a matrix, we have to find the orthonormal basis for the column space of A. Okay, so for this matrix, you let the first column be V1, the second column be V2, and the last column be V3. Okay, so from the lemma, we find U1, U2, U3 such that U1, U2, and U3 are what? Orthonormal. Okay, so to solve for U1, well, U1 is given by V1 over the norm. Okay, so the norm of V1 is given by this, that's square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. Okay, so U1 is given by 1 over 2. You see, you get square root of 4 is 2, so 1 over 2 times vector v1, that's 1 1 1 1. Okay, then the next step is to solve for u2. So before you solve for u2, you need w2. Okay, so you set w2 to be equals to v2 minus the inner product of this, supposed to be inner product. Okay, inner product of v2 u1 times u1. Okay, so we have v2 to be minus 1 4 4 minus 1 minus the inner product of v2 u1 is given by minus 1 times half minus half plus 2 plus 2 minus half. Okay, so when you're able to solve this, you will get you should get negative 3. Okay, so you should get 3, positive 3. Okay, then you multiply by u1. This is u1. So when you simplify this, you get 5 over 2, w2 to be 5 over 2 times negative 1 1 1 negative 1. Okay, then you divide w2 by the norm. Okay, so the norm of w2 is square root of 25. Okay, so you divide w2 by square root of 25 and you simplify. So after with the simplification, you get half multiplied by negative 1 1 1 negative 1. Okay, that's u2. The next thing is to solve for u3. Okay, so before you solve for u3, you need your w3, and w3 is given by v3 minus the inner product of v3 u1 times u1 minus the inner product of v3 u2 times u2. Okay, so you get this is v3, that's 4 negative 220. Then after you have simplified this, the second term, that's the inner product of v3 u1 times u1, you will get 1 1 1 1. Then the third term also gives us this. Okay, so when you are done, you simplify your results. So you get after simplifying your results, you get 2 minus 2 2 minus 2. Okay, so you get this. Okay, then you can factorize 2 out. So when you factorize 2 out, you get this. Okay, that's 2 multiplied by 1 minus 1 1 minus 1. Then now you can find your corresponding u3. So our u3 is given by w3 over the norm. So the norm of w3 is given by square root of that's 2 squared plus 2 squared plus 2 squared plus 2 squared. Okay, 2 squared is 4 4 4 4. So 4 plus 4 plus 4 plus 4 is square root of 16. Yeah, that's what we have here, square root of 16. Okay, and we know square root of 16 is what? 4. Okay, so to be 2 over 4, but you see 2 goes into itself once and goes into 4 twice, so we get half of 1 minus 1 1 minus 1. Okay, so we have generated our orthonormal set of vectors u1 u2 u3. You can verify. Okay, so that is that thing we have. Let's look at the exercise here. We have 2 exercises. Okay, so you can try your hands on these 2 exercises. Okay, but I would like us to discuss the second exercise, the exercise 2. Comparing the 2 exercises, I think exercise 2 would involves a lot as compared to the first one. Okay, so let's solve the second exercise. Okay, then at your own appropriate time, you can try your hands on the first one. Okay, so we have basis x, so that S contains 3 vectors u1 u2 u3. Okay, where u1 equals to 1 1 1, u2 equals to negative 1, 0, negative 1, and u3 equals to negative 1, 2, 3. We are to use the gram-schmidt process to transform S to an orthonormal basis in R3. Okay, that's the question. Good. So now we have u1 to be 1, 1, 1, u2 to be negative 1, 0, negative 1, and u3. Okay, so let's check if they are orthogonal. You see, u1 dot u2 is given by, so we have 1 times negative 1 is negative 1, 1 times 0 is 0, so plus 0, 1 times negative 1 is also negative 1. This gives us what? Negative 2. This gives us negative 2. So you have negative 2. Okay, so this means that u1, u2, and u3, they are not orthogonal, and hence they are not orthonormal. So we have to use the gram-schmidt process to transform these vectors u1, u2, u3 into orthonormal set of vectors. Okay, so first of all, we let our v1, okay, to be that from the lemma, we let our v1 to be the u1 over the norm. Okay, so this is u1. So u1 is given by 1, 1, 1. So we have u1 over the norm is the same as 1 over the norm of u1 times u1. So you have 1 over the norm of u1 is given by this. That's square root of 1 square plus 1 square plus 1 square multiplied by u1. Okay, so the norm is given square root of 1 square plus 1 square plus 1 square. They say what? Root 3. So you have 1 over root 3 times 1, 1, 1. And when you solve this, you multiply by 1, 1, 1, you get this. That's 1 over root 3, 1 over root 3, 1 over root 3. To solve for V2, we will need our W2, okay? So we let W2 be equals to U2 minus the inner product of U2 V1 times V1, okay? So this is our U2. The inner product of U2 V1 is given by, so this is U2 and this is V1. So we have negative 1 times root 3, get negative root 3, 0 times root 3, that's 0. The negative 1 times root 3 is negative root 3. You multiply by V1, okay? So when you simplify this, that will be minus 1, 0, minus 1. This gives us negative 2 root 3, but negative, because of this negative, we get positive 2 over root of 3, okay, times this, okay, that's V1. So when you simplify this, you get negative 1 over 3, 2 over 3, then negative 1 over 3, okay. That is W2. And we know that we can use W2 to solve for, find our V2. So our V2 is given by, W2 over the norm, okay, W2 over the norm. So this our W2, okay, so it's the same as 1 over the norm of W2 times W2, okay. So the norm is given by square root of absolute of minus 1 over 3 squared plus absolute of 2 over 3 all squared plus absolute of minus 1 over 3 all squared, okay. So now all times W3, okay. So when you solve this, the norm will be square root. You see, you have 1, we will get what? 1 over 9 plus 4 over 9. We get 1 over 9 plus 4 over 9 plus 1 over 9. And this is the same as 6 over 9, square root of 6 over 9. So it will be 1 over square root of 6 over 9, okay. But we know that square root of 6 over 9 is the same as 1 over square root of 6 over square root of 9, okay. And square root of 9 is what? Square root, we know our square root of 9 is what? 3, okay. So this changes to 1 over root of 6 divided by 3. Okay, so we can change this the division sign to multiplication. Then we find the inverse of the denominator. Okay, so you get 1 times 3 over root of 6. Okay, and this gives us 3 over root of 6. Okay, then you multiply by negative 1 on 3, 2 on 3, negative 1 on 3. Okay, so that will be our V2. Then the next thing is to find our W3 and use it to form solve for vector V3. Okay, so W3 is given by U3 minus the inner product of U3 V1 times V1 minus the inner product of U3 V2 times V2. Okay, so this is our W3, that's negative 1, 2, 3. The inner product of U3 V1 is given by this. Okay, and also V1 is given by this minus the inner product of U3 V2 is what we have here. Okay, times V2. So now we have negative 1, 2, 3. You see, minus 1 over root of 3 plus 2 over root of 3 plus 3 over root of 3 is 4 over root of 3. That's what we have here. Multiply by V1. Okay. Minus now 1 over root of 6 plus 4 over root of 6 minus 3 over root of 6 is 2 over root of 6. Multiply by V2. Okay. So we can multiply when you consider the second term. You see, the first term is given by negative 1, 2, 3. So for this, on the second term, you can multiply this vector by the scalar 4 over root of 3. Okay, so when we do that, 4 times 1 equals to 4 divided by root of 3 times root of 3 is 3. Okay, and it runs 2. So you get this. That's 4 over root of 3. 4 over 3. 4 over 3. 4 over 3. Okay. The same thing applies to the third term. Okay, we multiply through by 2 over root of 6, and when we do that, we get this. So now when you simplify this, you see you have negative 1 minus 4 over 3 minus, so that will be plus 2 over 6. Okay, so when you simplify it, you get negative 2. Let's consider the second element. That's 2 minus 4 over 3 minus 4 over 6. When you simplify it, you get 0. Then 3 minus 4 over 3 plus 2 over 6. When you simplify it, you get 2. So our W3 is given by negative 2, 0, 2. Okay, negative 2, 0, 2. Now we can find our V3. Our V3 is equal to W3 over the norm. And the norm of W3 is given by the square root. The norm of W3 is given by the square root of absolute of minus 2 squared plus 0 squared plus absolute of, let me write it well. So absolute of 2 squared plus the minus 2 squared plus 0 squared plus 2 squared. Okay, and this is the same as square root of absolute of minus 2 is 2. Okay, so when you square it, you get 4. 4 plus 0 plus 4, and that's square root of 8. Okay, so that's what we have here. So multiply. So that would be 1 over square root of 8 multiply by minus 2, 0, 2. Okay, and we know our square root of 8. 8 is the same as 2 times 4, and that's square root of 2 times 4. And this can, you see, we have root 8. Root 8 is the same as square root of 4 times 2. And this is the same as square root of 4 times square root of 2. Okay, but square root of 4 is what? 2. So 2 times square root of 2. And 2 times square root of 2 is given by 2 root 2. So you get 1 over 2 root 2 multiplied by negative 2, 0, 2. Okay, so when you multiply 2 by 1 over 2 root 2, 2 root 2, you get minus 1 over root 2, 0, then 1 over root 2. Okay, so therefore we have generated our vectors. Our newly generated vectors v1, v2, v3 are what? Orthonormal. Okay, the set v1, v2, v3 is what? Orthonormal. Okay, you can verify your answer if it's correct. So we verify that our newly generated vectors v1, v2, v3 are orthonormal. So first of all, we need to show that they are orthogonal, and also we need to show that they are unit vectors. Okay, so now let's pick distinct pair from the set v1, v2, v3. Okay, so v1 dot v2 is given by v1 transpose v2. Okay, so you have 1 over root of 3 times minus 1 over root of 6 plus 1 over root 3 times 2 over root 6 plus 1 over root 3 times minus 1 over root 6. When you solve it, you get 0. If you are finding the difficulty, you can watch my previous videos on inner product spaces. That will help you to understand it better. Okay. So the v1 dot v3 is given by v1 transpose v3. When you solve this, you get 0. v2 dot v3, that's v2 transpose v3, also gives you 0. Therefore, the set v1, v2, v3 is orthogonal set. Okay, the set v1, v2, v3 is orthogonal. Okay, that was first part of the verification. Now let's verify if they are unit vectors. Okay, so let's consider v1. So the norm of v1 is given by this, that's square root of absolute of 1 over 3 root 3 squared plus absolute of 1 over root 3 squared plus absolute of 1 over root 3 squared. And 1 over root 3 squared is 1 over 3 plus 1 over 3 plus 1 over 3. And when you add these three fractions, you get 3 over 3. Okay? And square root of 3 over 3. See, 3 over 3 is the same as 1. Okay? And square root of 1 is 1. Therefore, v1 is a unit vector. v1 is a unit vector. Let's find the norm of v2. So v2 is given by this. The square root of minus absolute of minus 1 over root 6 squared plus absolute of 2 over root 6 squared plus absolute of minus 1 over root 6 squared, right? So absolute of 1 over root 6 is 1 over 6. So when you square it, you get 1 over 6. Square of 2 over root 6, all squared is given by 2 squared is 4, and root 6 squared is 6. You get 4 over 6. And for the last term, you also get, that's absolute of minus 1 over root 6 is 1 over root 6. Okay, so when you square it, you get 1 over 6. So when you simplify this, you get 1 plus 4 plus 1 all over 6. They have the same denominator, so you can just add the numerators. Okay, so you have 1 plus 4 plus 1 is 6. 6 divided by 6 is 1, and root 1 is what? 1. So v2 is also a unit vector. Okay, now let's move on to v3. So you find the norm of v3, and it's also given by this, and when you simplify, you get 1. Therefore, v1, v2, and v3 are what? Unit vectors. Okay, and therefore, since v1, v2, and v3 are orthogonal, okay, we know that they are orthogonal, and they are also unit vectors. Okay, and therefore the set v1, v2, v3 is orthonormal. Okay, and since v1, v2, v3 is orthonormal, then we can say that the vectors, we have normalized or we have transformed u1, u2, u3 into orthonormal set of vectors. Okay, v1, v2, v3, using the gram-schmidt orthogonalization process.